welcome back everybody to the second session of our tutorial. So this session is about optimization on Riemannian manifolds. So the goal is to give you the basic tool to perform such kind of optimizations so that then you can apply them to your own approaches. So we will have a first part with the theoretical part in slides, and then the second part with practical and some code. Okay, so let me start with a motivating example. So let's say you have a robot, you observe a trajectory given by that robot, you observe position, velocity, acceleration, and you would like to basically design a controller such that the robot reproduces the observed trajectory. So here we have a controller which is based on impedance. So basically you have a stiffness which multiplies the difference between the target position x hat and the position in which your robot are, and then you have a damping gain kd, which is multiplied by the velocity, right? So what we want to do in that problem, very toy example, right? We want to optimize the stiffness such that we are able to reproduce the trajectory that we observe just here on the side. So what we can do is to define this as an optimization problem where we define a function of the stiffness. And what we try to do is to minimize the residuals between what the observed acceleration and the one that is produced by our controller, right? So this is the function we aim at minimizing. So as all of you now should know, these stiffness ellipsoids are symmetric positive definite matrices, so we have to define a constraint optimization problem such that the stiffness is actually valid, right? So we can do that with classical Euclidean tools, and we can use a semi-definite program with such constraints that ensure that the matrix is positive definite. And here you have the example of a trajectory that we obtain by optimizing the controller gain in such a way. Now we are in a tutorial about Riemannian optimization, so you may expect that what I will tell you is that instead of doing Euclidean optimization, what we can do is to consider this space of symmetric positive definite matrices as a Riemannian manifold. And instead of doing a constrained Euclidean optimization, we do directly an optimization on the space of interest, right? So this is the result that we obtain in dark blue, sorry. So you see that here, basically, first of all, our trajectory actually match better what we observed. And this is the cost. And you see that actually this Riemannian optimization reaches a lower cost. We can also have a look at what stiffness we actually obtain. So here you have in green, this is the ground truth, the one that we initially used to produce the trajectory. In blue, again, sorry, the one that is obtained via the Riemannian approach, and in orange, the one that is obtained via the semi-definite program. So you see that very obviously, the Riemannian one is actually closer to the ground truth. Now I have been playing a little bit around and I changed the initialization of my optimization. So I was really just playing around with that toy example. And here is the second result that you get if you put a worse initialization of your stiffness. What you see here is that we have this blue curve, so the Riemannian one, and you don't see the semi-definite program result. The reason for that is that in that case, you just don't get a result. You actually get one, but it's not valid. So you have some small negative eigenvalues in your matrix that is supposed to be positive definite. And basically, this is why here we get a completely flat ellipsoid. So I could have removed by hand those negative eigenvalue. I could have obtained a trajectory. But the point here is that even if you have a constraint, in that case, the optimizer was not able to satisfy the constraints. But the Riemannian one, again, was quite decent. Okay, so this would enter why we are motivated to use Riemannian optimization methods. Basically, we want to go from constrained problem in Euclidean space to unconstrained problem on a Riemannian manifold. And those Riemannian optimization methods are computationally superior in the sense that they give you better solutions and they actually converge faster with better properties than constrained optimization methods. So the outline is this talk. We're going to first talk about first order optimization algorithm. So essentially, this is the generalization of gradient descent-based algorithm to the Riemannian case. And in second part, we're going to talk a little bit about black box optimization algorithm. So starting with first order optimization algorithm. So first order optimization algorithm are based mostly on gradients. And this is what we're going to cover first. So this is a small recap how we compute gradient in Euclidean space, and then I will show you how this generalizes to the Riemannian case. So in Euclidean case, we have a Euclidean objective function, f of x, and x here belongs, in that case, to the plane, but it can be to a higher dimensional Euclidean space. And in an optimization problem, we are aiming at minimizing or maximizing this function. So the first notion that is interesting to go towards the gradient is the notion of directional derivative. So this is a scalar function, and it basically gives you the rate of the function, the rate of change of the function when you are at a point x and you move towards a direction with a velocity v, right? So it's literally you see the numerical rate of change of this function. And what we see here is the scalar, so the directional derivative multiplied by the direction in which we are going, right? Now, based on this, the gradient is the direction of the greatest increase of the function. So it gives you the direction in which you have to go to increase the function as fast as possible. And you have a relationship between the gradient in the directional derivative, which is given by the formula here, where the scalar, the directional derivative, is given by the inner product between the velocity at which you're going, the direction, and the gradient function. Okay? Now moving to the Riemannian case. In this case, we have a function on a Riemannian manifold, so it means the input of this function is on a manifold, in that case on the sphere here, and it gives you a scalar, right? So we define again the notion of directional derivative, and again the directional derivative is the rate of change of a function when you move through a point x at a given velocity v. This velocity v, in this case, is a tangent vector, okay? So it belongs to the tangent space, and this is how you measure the direction. And again, this is simply really the derivative of the function in a given direction. The Riemannian gradient generalized similarly. It's also the direction of the greatest increase of the function. And again, it's something that is defined on the tangent space at a given point. And in that case, we don't have a nice derivative computation for the gradient. We actually compute it based on the directional derivative. So the trick to compute the Riemann gradient is get the directional derivative, which you can get with this formula. And you know that it's equal to the inner product between the direction in which you're going. So the directional derivative is equal to the inner product between the direction in which you're going and your Riemannian gradient is the inner product on the Riemannian manifold. So again, with respect to the Riemannian metric. And once you have your directional derivative, you arrange it in the form here of the inner product and you extract that part. And this is how you get your gradient. Okay. Now let's say you have actually a coordinate expression for your manifold, and in that case you can have a formula that is a little bit easier for your Riemannian gradient, which is the following one. So what you can do is that you compute the Euclidean gradient of your function, or of a smooth extension of your function. That is, it's an extension where on the manifold the function is the same and then it smoothly extends. And then you multiply the Euclidean gradient by the inverse of the Riemannian metric, and you obtain your Riemannian gradient. Just to show you the proof of that, this is just a little bit of math. So you know that the directional derivative is given by the product of the direction in which you're going and the gradient with respect to the Riemannian metric. We can here replace the formula of the gradient by the formula we have above, right? So this is simply what you have here above. We know that the inner product on the Riemannian manifold is here V transpose times the metric times the second term. Here the metric and its inverse is equal to identity. You see that this is equal to V transpose times the Euclidean gradient, and this is equal to the directional derivative. We're good? Okay. There is another case in which the Riemannian gradient is actually quite easy to compute, and is the case where we have Riemannian submanifolds. So submanifolds, so N is a Riemannian submanifold of a manifold M if N is embedded in M. So example is the sphere that is embedded into one dimension higher Euclidean space, and the manifold N should inherit the Riemannian metric of M. So the example of this is the sphere, which is a Riemannian submanifold of R d+1, and in that case, the gradient is simply, the Riemannian gradient is simply equal to the orthogonal projection on the tangent space of the Euclidean gradient. So you have the Euclidean gradient of the function, and you orthogonally project it onto the tangent space, and this is your Riemannian gradient. The explicit formula for the sphere here is that one, where the orthogonal projection is simply given by the identity matrix minus x transpose, which is the point, the base point of the tangent space at where you are. So now we have a Riemannian gradient, so we can start playing a little bit and do some optimization algorithm. So the first optimization algorithm we're going to see is the Riemannian gradient descent. So again, I will quickly recap how it is in Euclidean space and then show you how it generalizes to the Riemannian case. So in a Euclidean gradient descent, you have an objective function that you want to minimize. And this is with respect to a variable x, which lies on the Euclidean space. So what you do, you start at the point x0, and then you iterate where you incrementally update x by starting from where you are at xk, iteration k, and then you basically do one step in the direction of the gradient. Okay, and you have these step ties that tell you how far you're going in the direction of the gradient. In the Riemannian case, we're optimizing an objective function, and here the input of this function belongs to a Riemannian manifold. Again, you start at a point on the manifold, this is important, and then we have this iterative process, where basically your next iteration is given by the exponential map at x, so where you are, in the direction of the gradient scaled by a given step size. Okay? In pictures, what it gives, you are at your current iteration here, xk. You compute your Riemannian gradient on the tangent space. This is this blue vector. Here you have so it's minus the Riemannian gradient, right? The blue vector. You scale it by your step size, and then you use the exponential map to map your vector, the direction in which you're going from the tangent space onto the manifold. Okay? And then you obtain your next iterate, you compute the gradient again, and you move on in that way until you converge. So the interesting properties in this algorithm is to check, for optimization people, it's important to check basically how this converges. So to analyze the convergence of this Riemannian gradient algorithm, we have to do two assumptions. The first one is that we are optimizing a function which has a global optimum, right? What that simply means is that you have a point basically where the function is smaller or equal to the function at all other points. And the second assumption that we have to do is the L smoothness assumption. So this is a generalization of the L smoothness assumption in Euclidean spaces to Riemannian manifold. So the idea is that your function f should be differentiable, and basically its gradient is called L Lipschitz. So what this means intuitively that the function is continuously differentiable, and the rate of change of this function is limited, right? So what we see here is that when we do basically the difference between the gradient at x and the gradient of this function at y, parallel transported in the tangent space of x, so that we can compare the two gradients, this difference, which is given by the Riemannian norm, should be smaller than the Lipschitz constant times the distance, the Riemannian distance, right, between the point x and the point y. So the rate of change of your gradient is basically limited by this Lipschitz constant. All right? This is for the sake of the proof that I will show you in a minute. We can rewrite this L smoothness assumption a little bit differently. This is just really playing a little bit around with the formula above, and this is an equivalence. So now if we define our Riemannian gradient descent with a step size given by 1 over L, L being the Lipschitz constants, which you have then here above, the convergence is given by this. So you see that the norm of the gradient at iteration k is smaller or equal than the square root of the value of the function at x0, so where you started your optimization, and the value of the function at the optima. And this is scaled by the Lipschitz constants and divided by the number of iterations. Okay? So what that also means is that basically when you have an infinite number of iterations, you are sure that the norm of your gradient is converging to 0. So basically your optimization algorithm converges. The proof of that, So we start with the second assumption, sorry. So with the formula that we have there concerning the L smoothness. Here, basically, y here is equivalent to x at iteration k plus 1, and x is at iteration xk. And here, basically, the log of this is simply equivalent to the gradient because of our descent formula that is here. Okay, we can rewrite a little bit this, and then we can simply see that the difference between the function at iteration k and iteration k plus 1 is bigger or equal than 1 over the Lipschitz constant times the norm of the gradient. And then we use the first assumption, which says that basically any point in the function at any point is bigger or equal than the function at the optimal, and then basically it means that f at x0 minus the f at the optimal x is bigger or equal than the difference here, which we can rewrite as the sum of all the differences across all iteration, which using then this formula here, we obtain the convergence that we had above. Okay. Now we can make one additional assumption, is that our function is geodesically convex. So geodesically convex is literally the generalization of convexity, but to a function that is on a Riemannian manifold. So intuitively, it means that when you have a geodesic on your manifold, and you check the value of the function along this geodesic, this value of the function is convex. Okay, so this is the value of the function in black along this path, and you see that when you draw a straight line, the function is convex below. And when you make that assumption, the rate of convergence is given by the equation that you have here. So the difference between the function at the initial point and at the optimum is smaller in a range of 1 divided by your number of iterations, basically. What is very interesting here is that these convergences are exactly what you obtain when you have a gradient descent on the Euclidean space. So it means that by using Riemannian gradient descent, we're able to have the same convergence guarantees that Euclidean gradient descent, but we are working on a curved space. Yeah.
How restrictive is the assumption of geodesic convex?
Sorry?
How restrictive is the assumption of geodesic convex?
So you can see it as restrictive as when you have in Euclidean space a convex function. So it's really a subset of the problems. It's really literally the generalization of that. So it's restrictive for sure, but then you have a nice convergent property for that function. Yeah. You're welcome. Okay. So with that, let me give you a little bit of a general view on first-order optimization algorithm. So when you think about Euclidean optimization and you do a first-order optimization algorithm, the first thing that you do is always you update your search direction. In the case of the gradient descent, your search direction is just minus your gradient, right? But in many algorithms, the search direction is actually a function of the gradient and of the previous search direction. We'll see an example of that also in a minute. And then you update your estimate simply by subtracting a step size times your your search direction, sorry, of your current iterate. Now to generalize that to the Riemannian case, what you also do first is you update your search direction. You see that here we have a different letter for the previous search direction. The explanation for that, it comes in the third step. But the idea is, again, you have basically a function which combines your Riemannian gradient and the previous search direction. And then you update your estimate. And again, we use the exponential map, okay, because this vector lies on the tangent space. So we go from the tangent space to the manifold. And the last step is the one where we actually move our previous search direction from the tangent space at the previous iterate to the tangent space of our current iterate. This is actually very important, okay? It's again the fact that tangent vectors belong to a specific tangent space, and when we change tangent space, we have to move those vectors to the new one using parallel transport, okay? This is very important. So an example of one such generalized algorithm is the Riemannian conjugate gradient descent. So here, again, we want to minimize a function f with respect to a point on the manifold. We start at the current iterate. We are given an initial search direction. The first thing that we do is to find the next iterate. So in that case, we actually solve a line search problem that gives us our step size. Okay, so until what is the step size we have to actually make to have the best possible update. Then we have the exponential map step where we are finding the next iterate, and then we find the next search direction. And what we do here is what I just told you before. We first parallel transport the previous search direction from the previous tangent space here to the new tangent space here of our new iterate. And then in that case, the next search direction is given by a combination of the new gradient and of the parallel transported new search direction. Okay, and then we iterate these until we converge. Okay, so one type of approach that is nowadays very, very popular, especially for machine learning, is Riemann and stochastic optimization. Again, I will show you first a Euclidean case and then the Riemannian case, and we're going to start with the very simplest possible stochastic algorithm, which is stochastic gradient descent. And then I will show you how we can go to more complicated algorithms, which are more in the range of Adam, AMS grad, and that kind of things when we want to do optimization on Riemannian manifolds. So for the Euclidean stochastic gradient descent, as usual, we want to minimize a function f, which has an input on the Euclidean space. The point here is that we have a function f that has an expensive gradient computation, okay? Typically in machine learning, you can think about you have many data, and if you have to compute at each iteration step the gradient for all your data, it becomes very expensive. So usually what we do is that we actually compute the gradient only for a subset of those data. This is the principle of mini batches. So the assumption of Euclidean stochastic gradient descent is that basically the expectation of a randomly drawn realization is equal to the function itself. When I say here randomly drawn realization, you can really think about I'm taking just a subset of my data for each iteration step, randomly sampled, right? So you have a full batch of data, you just take some few, you do an update, at the next step you take another batch, etc. in that sense. So this assumption also gives you a result on the gradient, that basically the difference between the real gradient and the gradient of your randomly drawn generalization is 0, the expectation of that. So then the stochastic gradient descent works similarly to the gradient descent one. So we first update the search direction by using the gradient of a randomly drawn realization C, and then we update the estimates, and we iterate those two steps over and over again. Now the Riemannian generalization, so this Riemannian stochastic gradient descent algorithm, is very similar in the sense that we are aiming again at minimizing the objective function. This objective function has an input on a manifold, and we have an expensive gradient computation. So in that case, we again assume that the expectation of a randomly drawn realization is equal to the function itself. And again, we can assume based on that, that the difference between the gradient and the gradient of the randomly drawn realization is equal to 0. So again, we update the search direction. So in this case, we have the gradient of the function, the Riemannian gradient of the function of the batch of data that we are choosing. It still belongs to the tangent space, and then we update the estimate via the exponential map. Again, we can have a look at the convergence properties of this Riemannian stochastic gradient descent. So here we have, again, this assumption of having an optimum. We again have this assumption of having a smooth function, Lipschitz smooth function. And we have an additional assumption that says that the gradient of any drawn realization is always bounded. The expectation of this gradient is bounded by a constant. Then when we take this Riemannian stochastic gradient descent algorithm, you see that here we have a step size, which is a constant divided by the square root of the number of iterations. We obtain that convergence property. So that the expectation of the gradient over randomly drawn realization is basically smaller or equal than 1 over the number of step size, the difference between the initial function and the optimal function, and we have here the Lipschitz constant that appears again, and the bounding of the gradient. And again, this is nice because it's the same as Euclidean. So again, you have nice guarantees, which are the same as for Euclidean algorithm, but here you are working with Riemannian data. So I told you before, this is kind of the simplest stochastic algorithm that you can have, but we can also generalize to many other classical algorithms that are used now typically to optimize neural networks, right? So here I will briefly show you the version of AMS grad. This is basically a slight modification of the Adam algorithm that is really widely used, simply to allow to have the convergence proof. I'm not showing you the convergence proof here, but it is on the paper that is referenced here at the bottom if you want to have a look. So the idea of AMS grad is that for each iteration, basically you compute first the gradient of your function, and then you have here the momentum term, which is equal to the previous momentum term plus some multiplication of the gradient. So this is basically the direction of update. And then you have a second momentum vector, which is given here by v, again as a function of the gradient. And based on that, of that two momentum vectors, you have a projection. So the next iterate is equal to the projection of the previous iterate scaled by the two momentum vectors that you have there. Generalization to the Riemannian case, you use the Riemannian gradient instead of the Euclidean one. You use here the exponential map instead of using the minus sign. And the momentum are basically computed using here the parallel transport. So you have to parallel transport your previous momentum to the tangent space of the new iterate. So principles are very much the same. Okay. So that was what I wanted to tell you concerning first order optimization algorithm. And now I will move to black box optimization algorithm on Riemannian manifolds. So why black box? Simply because when we are in robotics and we want to do, for instance, manipulation, this involves skills that require the pose of the robot to be precise, or that could require, for instance, the robot to be stiff in specific directions. In addition, we would like to be able to always cope with the uncertainty of the task and to generalize the skill to new situations. So for instance, if you take the orientation skill on the left, you may want, if the orientation of the hole changes, to actually adapt your skill and have a new orientation of your end effector. In the second case, you may want to change the stiffness of your robot through the task, such that at the beginning you have a large stiffness in a direction, and at the end you have this stiffness adapted to insert the peg in the hole. So basically, controllers and policy parameters often have to be refined or adapted. And in robotics, we would like to have a safe, a fast, and a data-efficient learning process, right? So for that, an algorithm that is well adapted is Bayesian optimization, which is a very well-known instance of black box algorithm. And what we would like to do here is to exploit domain knowledge in the form, in our case, of Riemannian geometry to improve the data efficiency of this process, right? So domain knowledge has been exploited in BO in different cases, and usually this is something that works well to improve the data efficiency. So what we aim at doing here is generalizing Bayesian optimization to Riemannian data, such that we are able to, in an efficient way, optimize policies that are defined based on Riemannian data. So I will give you a quick overview of what BO is, again, in Euclidean space, so we are all on the same page, and then I will show you basically the tools that we need to be able to generalize it to the Riemannian case. So again, we have an objective function f, and we are trying to minimize it. And the idea here is that objective function is black box. That means that we don't have a closed form solution for it. We cannot really compute gradients, but we can observe this objective function through the full parameter space. So you can, for each parameter, test it and get a value of your function. So what Bayesian optimization does is to model the objective function, typically with a Gaussian process. So we put a prior over the function, and then the posterior of the Gaussian process gives us a mean estimation of our function, as well as an uncertainty estimation, right? Which is given here by, this is the mean estimation, and this is the uncertainty, which is big where we don't have data. The second step is to evaluate the utility of candidate points with an acquisition function. So basically, we want to know which point we should test next to be able to minimize our function. So we define an acquisition function, we maximize it, and the next point is given at the maximum of this acquisition function. The idea here is that the acquisition function is defined based on the Gaussian process. So basically it trades off between the mean of the Gaussian process. So we are trying to query where the mean is low to eventually have a lower estimate of the function. and where the uncertainty is big to be able to explore where we don't know how the function behaves. So we iterate this, and usually BO converges quite quickly in some few iterations to the global optimum. So now let's say we want to have basically a function that we optimize, but our input belongs to a Riemannian manifold. So we have here to take into account two main points. The first one is that the Gaussian process is completely specified by its mean and by the covariance matrix that we put there. Usually the covariance matrix is represented using Euclidean distances, and as you may know by now, Euclidean distances are not great to represent the behavior of data on Riemannian manifold. So what we will do here is to design Riemannian Gaussian processes through the use of Riemannian kernels to be able to consider data on Riemannian manifolds. The second point is that the quality of the next query point depends on the optimization of the acquisition function. And as I just explained to you, instead of using a constraint optimization, we better use a Riemannian optimization, which is unconstrained and better and behaves with better properties. Okay, so I will now explain you how we do the first step. I think the second step you already got a quite good idea, and then I will show you a couple of results to show you how useful it is to actually consider the geometry of your data when you do that kind of optimization. So quickly, Gaussian processes in Euclidean space. A Gaussian process is used to model a function which is potentially noisy, and what it does is that it places a Gaussian prior over function. So you say that your function is modeled by a Gaussian distribution given by with the mean, which depends on where you are, and by a covariance function, which depends also on x. The idea here is that when you're given a set of noisy observation of your function, you can refine your model, and you compute the posterior, so the joint distribution of the data that you observed, which are the uppercase x, and this is the new data point, the new input for which you would like to know the value of the function. Based on this joint distribution, you can compute the conditional distribution, and now you obtain the value of the function at an unknown input, which depends on the previous points that you observed. And this is again given by a Gaussian distribution, which depends on your mean function, and this depends on your kernel function. Right? So you obtain then, when you have that kind of observation, this is the kind of value that you obtain for your function, where again you have the mean here in black, and this is the uncertainty which is given by the covariance function, which you have there. Okay. So this covariance function, the kernel functions, are typically given, I mean, there is a wide range of kernels. You can choose among a lot of available kernel, but the ones that are very often used are the Mattern kernels, which are given by the formula that you have there. And basically, those have three parameters. So they depend, first of all, they are stationary. That means that they depend on the distance between two data points that you're considering, x and y, which you have here as input. And then this depends on a length scale value, a variance value, and a smoothness parameter. And this equation actually simplifies when the smoothness parameter is equal to an integer plus 0.5, right? Which is what is often used. So the smoothness tells you how smooth your estimate of your function will be. So here you have some randomly drawn realization of the function, and you see that they are very noisy. This is because the smoothness parameter is very small. When you put the smoothness parameter towards infinity, you obtain the so-called squared exponential kernel, or RBF kernel, that is even more well known, which is simply here the exponential of the distance between the 2 points. And basically, this is weighted by a length scale function and a variance function. Okay, and this function is infinitely smooth. Right? So this was Euclidean Gaussian process. Now we want to again go towards Riemannian Gaussian processes. So here we have two possibilities of extension. The first one is where we say, okay, we have a function that has a manifold value input, right? So x belongs to a Riemannian manifold. And the second one is we say, okay, in that case, we actually have an output of the function that belongs to the manifold, and there is also an extension for that. In both cases, we have to take into account that the Gaussian process is specified by the mean and the kernel function, so the modification to the Riemannian case all will go there. So in the manifold valued input case, we design kernel for Riemannian manifolds, and in the manifold valued output case, we define a mean function on the manifold and multi-output kernel to be able to take into account the correlations between the different dimensions of your manifold, basically. So I'm going to focus on the first case because this is what we need for Bayesian optimization. But if you're interested in the second case, you can check the reference that is here. So again, we have Gaussian process with manifold value input. So we are trying to model a function that has an input lying on the manifold and a scalar output in that case. And basically here we again put a Gaussian process prior on it. That means the input is on the manifold, the mean function outputs a scalar, and the covariance function here takes as inputs 2 points on the manifold. We obtain again a conditional distribution once we have data that are known, this data here, and you see that this has the same shape as for the classical Gaussian process. Again, the difference is that you have manifold valued inputs. What we need here is kernels that actually allows us to express the similarity between data on manifolds, right? So what the kernel tells you is really how similar your data point is, and this is here what we want to change. So a very naive way to do that is, let's say, okay, we take the Euclidean squared exponential kernel, which depends on the Euclidean distance, and let's just replace this Euclidean distance by the geodesic distance on manifold, right? This should allow us roughly to take into account the geometry of the data. The issue here is that this kernel matrix is not positive definite for all the value of beta here, which is the inverse length scale. And for a valid Gaussian process, this kernel function must be positive definite. This is really a strict requirement. So what we can do is to observe that the minimum eigenvalue function that tells you if the kernel is positive definite or not is continuous. So, and that the limit, when we have basically this beta here that goes to infinity, the kernel function will always be equal to identity. And as the function is continuous, that means that you can find a minimum value of beta. If you have your beta that is higher than that, your kernel is going to be always positive definite. So you can basically do is to determine this beta mean experimentally, right? So you sample many points, you check for which value of beta all your kernels are positive definite, and you choose beta such that experimentally you get always positive definite things. So this is a naive case. It kind of works sometimes, but it's still not great, okay? To show you why, you can see here the example of a kernel on a circle. So the manifold is a circle. And in that case, the naive generalization takes into account the distance between the points, geodesic distance. Now, if we fully generalize those kernels, as I will show you in the next slide, this is the kind of generalization that we obtain. So you see that basically we have a sum of terms which account for the distance between the 2 points. The first term, where n is equal to 0, is exactly the same term as what we have above. But then the complete generalization actually takes into account not only the shortest path, but all the possible paths between the points on the manifold, right? So when n here is equal to -1, we have the reverse path. When n is equal to +1, we have the shortest path plus 1 full tour of the circle, and etc. when we have n that are growing up. So the naive generalization is like obvious somehow, but it's actually only locally correct because it takes into account only the first term of the entire summation that is obtained when we properly generalize the kernel to the Riemannian manifold. So to show you how we actually generalize the kernel properly, we have to take into account an alternative view of kernels. So a kernel function is actually given as a covariance of a random process, this random process f in that case, and the random process satisfies a stochastic partial differential equation. The stochastic partial differential equation is composed of the white noise on the right side, and on the left we have the Laplacian of the random process f. Yeah, exactly. So the Laplacian, and the k that you see here is again the length scale parameter, right? So we want to generalize this to compact Riemannian manifolds. So this is the case where we have the sphere, the torus, and SO, for instance. We can generalize this equation in the following way, where we replace the white noise by the white noise with respect to the Riemannian metric. So you see, we see again here this Riemannian metric. It always comes. It really defines everything, right? And on the left side, we have the generalization of the Laplacian operator to Riemannian manifold, which is called the Laplace-Beltrami operator. And again, it's defined based on the Riemannian metric. The g that is here on the function is the Riemannian metric. So you see that again here, we depend on the Riemannian metric to define all the geometric tools that we need. What we do here is that we solve this partial differential equation, then we compute the covariance of it, similarly as what we did here for the Euclidean case, and then we obtain the following summation that describes kernel on Riemannian manifolds. So you see here that we have basically this lambda and fn, which are the eigenvalues and eigenfunction of the Laplace-Beltrami operator. It has to be computed differently for each manifold. And then we have again here the length scale, and this is the variance parameter, and this is just a normalization constant. And this could actually remind you of the Mercer theorem in Euclidean space, which tells you that a kernel in Euclidean space is also a sum of eigenvalues and eigenfunctions. So this is the case of the squared exponential kernel with infinite smoothness. You have a similar result for the Mattern kernel with any types of smoothness. So to show you a little bit intuitively how it looks, so a prior of the Gaussian process look as follows. You have here in the Euclidean space, it's basically a constant mean, and this is the uncertainty given by the kernel function. So in in Riemannian space, you have a constant mean, a constant variance here, and then we can also draw prior sample from our Gaussian process. And once we have observations, so here in red, here in black, the mean of the kernel of the function changes. We can also compute the variance. So you see that here the variance, the color changes when we are far away from the data. So again, we have higher uncertainty far away from the data, and we can again draw posterior sample on the GP. Okay. That was the case of compact manifolds. So intuitively sphere, torus, and SO in the ones that we covered. But we may also want to use non-compact manifolds, so to have kernels for manifolds such as the SPD manifold, the hyperbolic manifold, and several others. So the framework I showed you before is not valid for non-compact manifold, and here what we can do is to use instead the definition of heat kernel, which is actually, so the squared exponential kernel is obtained as a rescale reparametrized heat kernel. So in the case where you can obtain this heat kernel from the equation that you have here above, then you can rescale it here, and you see that this is the squared exponential kernel that you rescale, and it's equal to the heat kernel. So you can do the opposite process. And in the case of non-compact manifold, this equation, you can solve it, not always easily, but you can solve it, and then if you rescale it, you obtain the squared exponential kernel. In Euclidean space, this is how it looks. The heat kernel has the shape here on the left, and the squared exponential kernel has the shape here on the right, and you see that you basically rescale the length scale parameter here, and you put another constant in front, and they're equivalent. Then if you want to have Mattern kernel, you define them as integral of squared exponential kernel following this formula that you have here, and you can then obtain different types of Mattern kernel for non-compact manifolds. Okay. So this allowed us actually to do the first step to modify our Bayesian optimization algorithm. And the second step, optimizing the acquisition function, is exactly what I discussed during the first part of the talk. So we don't change the formulation of the acquisition function, but we actually use Riemannian optimization techniques to optimize this acquisition function, right? You can use first order methods, as we showed in the first part. It's completely fine. You can basically pick what works best for your application. So let me show you, this is the final algorithm. So basically for Bayesian optimization Riemann manifold, you are given a set of initial observation. Your goal is to give the final recommendation of the minimum of your function. You update the parameter of your Gaussian process. Then you optimize the acquisition function to find the next query point. You query actually the objective function with the next query point. You augment the observed data, and you iterate until it converges. So let me show you an example of how that works. Here we have a benchmark function on the sphere, which is the Ackley function. Basically, the optimum of this function is the star that you have here, and the color tells you how low or high the function is. And what I will also show you is 2D projection of this function. So here you always see x1 and x2, which are the 2 dimensions there. Here x2, x3 with the last dimension here. And here the vertical axis is the value of the function, right? So again, you have your optimum here, and this is the landscape of your function. We aim at finding here the global optima of this function, and what I will show you is how the Gaussian process mean evolves on the sphere, and how the Gaussian process mean and variance evolve on the 2D projection. So the variance here is given by this gray envelope that you see. And here we already have observation. You see that the variance is very tiny where we have observations. And again, we aim at actually finding this optimum. And I will show you the evolution of the value of the function through iterations. So you see here we started the Bayesian optimization, and quite quickly the Bayesian optimization exploits and converges to something that is quite close to the ground truth optimum. And then there is an exploration phase where we are querying points in high uncertainty zone. And you see that here basically after 15, 20 iterations, we already have something that is very close to the optimum. And after 45, 50 iterations, the landscape of our function that will come back is actually very close to what we observe here on the left. Exactly, so here we are at roughly 30 iterations, and you see that we are really starting to approximate this function quite well. We can have a look at how this converges. So here we have convergence statistics for several functions on several manifolds. So starting here on the sphere of dimension 5 for the Levy acquisition function, Levy optimization function, sorry. So here what you see is you have here different types of kernel. This is the naive one that I showed you at the very beginning. Then we have the Riemannian squared exponential kernel, the Euclidean squared exponential kernel, the Riemannian mattern, and Euclidean mattern, right? And in the Euclidean case, what we do is that we use the Euclidean kernel and we use a constrained Euclidean optimization algorithm for the acquisition function. The goal here is basically that those convergence curves should go as low as possible, as fast as possible, with as few variants as possible across different initialization. And what you see is that basically the three ones that are converging the best are the two Riemannian ones and the naive generalization. So here the naive generalization performs well because our function is actually varying quite slowly, so it's still a good approximation. The function is evolving quite fast, so it's still locally a good approximation of the Riemannian kernel. Here we have some convergence on SO3, and you see that again the Riemannian kernel is the one performing the best, again on the symmetric positive definite matrix manifolds, and here we have a case where the naive approximation again performs properly. And finally on the hyperbolic manifold, and here you see a very clear difference between Euclidean and Riemannian optimization. So basically considering the geometry of your data for this problem leads to faster convergence, better accuracy, and lower solution variance. Let me show you now a brief example of an application of this. It's rather a toy example, but I think it gives you a good idea of what you can do with such methods. So what we want to do here is to basically have a velocity controller where basically we ask a planar robot to follow a vertical line going down. And we would like this robot to be able to follow this vertical line with a quite high speed. And for that, what we do is that we propose to track the manipulability of the robot. And we would like ideally the manipulability to be oriented towards the path of the robot such that the robot is actually able to apply a high velocity to move along this line. So in that case, we are trying to optimize the desired manipulability that you can see here, m hat. And this is the one that is tracked by the manipulability controller that you can see there. This is the objective function we are minimizing. So we would like the robot to be able to follow this trajectory with a low end effector jerk. We would like to have the manipulability aligned with the direction of motion of the robot. And we would like to be able to precisely track a manipulability. Because if we put a desired manipulability that is untrackable, I mean, there is no point, right? So here you will see several iterations of the Bayesian optimization. The robot tracks the vertical line. You see the desired manipulability in green that we are optimizing and the current one in purple. And you see in those first iterations that basically we have desired manipulability that the robot cannot really track. And when we move on, we actually, the objective function here starts decreasing, and you see that the manipulability we get gets oriented towards the direction of motion vertically, and is getting trackable actually by the robot. And after 100 iterations, this is the desired manipulability that we obtain with Bayesian optimization. So you see that in that case, we can track the vertical line, the robot tracks the desired manipulability, and this manipulability is aligned with the direction of motion. In terms of convergence statistics, same as before, right? So we have here the Riemannian kernel, which is the one that performs the best, followed by the naive kernel approximation, and those are mostly Euclidean approaches. So again, we converge better, faster, and with lower solution variance. So main references for Riemann optimizations, they are the same as what I gave at the end of the first talk, but for those who were not there, there is the book by Pierre-Antoine Abzil and his colleagues, and there is the new book by Nicolas Boumal, and both are actually very, very nice if you're interested in optimization algorithm on manifolds. In terms of libraries, some of them, I showed them to you also before. There is again this manopt with MATLAB, Python, and Julia backends. There is geopt for stochastic gradient descent. So the stochastic gradient descent I presented is implemented there, as well as Adam and a couple of other stochastic optimization algorithms. This is super handy to use if you want to train networks or anything with PyTorch. You can really plug it on top. It's actually great. There is the same equivalent, but with TensorFlow, for those of you who are using TensorFlow. There is here GeoTorch, also for Riemannian gradient descent and integration with PyTorch optimizers. ReopJax for the ones that are using JAX. Yeah, so I think with those, you can really have a nice overview of what to use depending on what language you're using. And with that, thank you for your attention, and I'm happy to take questions. And I think you don't have it on. Yeah, just the small, yeah, you
Top.
put it up.
Here we go.
Exactly. Yeah.
So first of all, not only was that a great tutorial technically, but I think you gave a great tutorial on how to give a tutorial. That was amazing. So thank you so much. So first, a big picture question, then a technical one. So I'm assuming there's least squares methods for all of this. And so I'm wondering if, like in those books, are there like least squares type problems on Riemannian manifolds?
Yes.
Okay, perfect. So I'll look those up. Now, for my technical question, I noticed in the gradient you have G inverse. Mm-hmm. So my knee-jerk reaction is to avoid inverses at all costs. So I guess my question is, and I know you talked about the whole subgradient method. So my question is like, I would then default to that always personally to avoid an inverse of G. But can you give me some insight onto, can you avoid this? Can you pre-compute this? Is it not a big deal? Yeah.
Mm-hmm. Okay, so maybe first of all, you cannot always default to the second one. So the second one is really in the case where you have an embedded submanifold, and this is not always the case. So if you can use that, it's usually what is implemented in the optimization libraries. When it's possible, this is what they have, but you cannot always do that. In terms of computing the inverse, what's often happening is that the Riemannian metric doesn't get crazy. Neither too small, neither too big, at least for the smooth spaces we are dealing with. So numerically, you don't have too much issues. Okay, it's computationally a little bit expensive, but it's not really a big deal. Does that help a bit?
Yeah, perfect, thanks.
Okay.
So my question is, could you give me an intuition for why, if you use the sort of the naive geodesic definition, the kernel loses its definiteness? Can you give me an example of how that can happen? Because I don't quite see how then if you include sort of all the other all the other eigenfunctions that resolves it. Right? It's because I can't see the obstruction. So maybe can you explain the obstruction?
So technically the reason is definitely because you're not considering all the terms. And do you remember?
So let me see if I understood. So I think you're wondering at which moment the kernel is not anymore posi-definite?
That's right.
Yeah, so the point is that not because we have a distance function on the exponential kernel means that for all values for the covariance, you're going to ensure that for that distance function, you're going to have the full covariance with all eigenvalues greater than 0. So that's kind of the abstraction of that. Of course, that posi-definiteness constraint not only depends on the distance, but also on the beta value that we have there to be able to ensure that it's always posi-definite.
Okay, so it's not actually a geometric property. It's a property of, I guess, of the parameters that you choose somehow.
For the naive version, yes.
Yeah.
Yes.
Okay. All right. Thank you.
Yeah. I think at the end of the day, it's quite, when you use kernels, you always have to prove this positive definiteness, and this is not always easy. And there is here a proof really that shows that actually it's not positive definite. Yeah.
Hi. So in all your Bayesian optimization, or you're using the maternal kernel for Riemannian. So you have to compute the Laplacian, right, for all the maternal kernels. For
sorry?
the Laplacian. So how do you compute that? It seems like you need still information about the function f of x.
I'm not sure if I fully got it. Let me go back maybe to...
So for the experiments that Noémie showed, so we do have benchmark functions for which we actually know the optimum. So for example, the Ackley, the Levy, so these are typical optimization benchmark functions. So we do have the ground truth for that. So we can compare how close the optimum that is found by BO is to the global optimum. Is that the question that you're asking, or?
But okay, this is a black box optimization, right? You don't have access.
Yes, but it's like we were assuming that. So we in this case it's true. Like we do know the function because it's a benchmark function, but we're still sampling, and we have the ground truth anyways. So it's how we actually benchmark the BO.
I'm not sure if the confusion comes from here where you have this F. That's what you were asking, or?
Yes, yeah.
Okay.
Okay, you're using samples of.
This is not the function. It's the Laplace Beltrami eigenvalues. That it doesn't depend on the function.
Okay, got it. Thank you.
Well, also from my side, congratulations for a fantastic tutorial. Related to the casting of this, when you talk about the change of a function, the natural way would be to use one forms because you don't need to talk about metrics at all. So the gradient, let's say the way to talk without metric would be the one forms. Can you recast everything without, in that setting, because then you would not need to invert the metric basically, right? Anytime. Have you looked at that?
So I haven't looked at that, and it's true that they don't talk about that neither in the books on optimization that we cite. I'm not sure why, and I'm not sure if you can recast that problem in that way.
Okay.
That's actually a good question.
And the second one I have is when you talk about the covariance, covariance is, tensorially speaking, is 0-2 tensor, so you cannot take eigenvalues of it unless you have a metrical way to rise the index, so to speak. Do you use the metric in order to do that in some way? Or how does that work? Because you cannot take eigenvalues of a quadratic form.
So you mean when we are computing the quadratic values of the kernel?
Yeah,
right?
so you talk about eigenvalues of the covariance, right?
Yeah.
And I mean, you can, in principle, if you don't have a Riemannian way to rise the index, you can't. It's not an invariant way of... So do you use the Riemannian structure in a way or another to do that?
So I think the covariance here is a little bit different than, it's not the covariance between data on manifolds. So for each couple of data, you get a scalar number, and then what the Gaussian process does is that it puts all that in a covariance matrix.
Yeah, but it's a quadratic form, so you cannot take a eigenvalues of a quadratic form or a matrix or a mass, inertia, things like that. So probably use the Riemannian structure in order to do that, I suppose.
So I'm not sure you're referring to the eigenvalues that we compute for the kernel?
Yes, so I mean, eigenvalues, you cannot take eigenvalues of a 0-2 tensor, of a quadratic form.
Because I think is what we are referring here for constructing the kernel is basically the eigendecomposition of the Laplace Beltrami operator.
Well, so, maybe it's too technical. Let's talk later.
Yeah,
okay.
let's take it offline.
Yeah, thanks.
I would have two questions. So one a bit more out of curiosity. Is there some intuition about the exponential and log map, like how it is connected to the exponential we know with the infinite series?
No, in that case, not directly. So I think it is connected, but in the Lie group case, not in the manifold case, in the Riemannian case.
Yeah. Okay, and then a bit more practical question. So is there the same kind of extension of the second order type optimization, like with Newton type methods, as with gradient descent, or are there additional difficulties to take into account?
Yes, yes, definitely. So they are extension of second-order methods. You can also find them in the books that we mentioned. The only kind of thing that you still need to extend is the Hessian function. So basically what they do first is that you generalize the Hessian function to the Riemannian case, similarly at what we did for the gradient. And then you are using this generalization in the second-order optimization algorithm. That's the main point.
Thank you.
You're welcome.
Thank you for the talk. So I have a quick question about practical. So you also show that you need less iteration to converge to the global optimum. But I just wonder, is it the complexity of each iteration also? I just want to know the some feeling about us, because it's obviously increased complexity in each iteration. Mm-hmm. So do you have any plots for that also?
Yeah. So it's true that the complexity, numerical complexity of each iteration is a little bit increased because you're using exponential map, parallel transport, and Riemann gradient. This is true. In practice, what happens is that the reduced number of iteration that you do usually covers this additional. You still have a lower optimization time than if you do Euclidean Euclidean approaches, because you need more iterations. Plus, on top of that, you have those convergence guarantees that you don't have if you use constraint optimization in Euclidean spaces, and you usually reach better solutions. So at the end of the day, the global property of Riemann optimizations are superior to the ones of constrained Euclidean optimization algorithms.
Thank you.
So if I may add, something that actually is relevant for the practical use of Bayesian optimization is the fact that in practice, for physical systems, each iteration, so each parameter that we try, is very costly. So here the priority is actually to lower the number of iterations, but we actually don't care so much if each iteration actually is costly to evaluate. So in that sense, like the cost of the Riemannian case, even if it's like one order of magnitude, I don't know, I'm just guessing here, more costly than the Euclidean case, is not a problem, because we actually want just to make the convergence actually faster in terms of number of iterations.
Okay, thank you very much.
Okay, thanks a lot for the very nice tutorial. I was wondering, it was very nice to see that all the algorithms that are defined on flat space can be lifted in a sort of curved Riemannian space. I was wondering, is there any Riemannian native optimization method that kind of degenerate on a flat space? So is there something that curvature gives and that flat spaces do not have?
So I think most of the work that is done on optimization on Riemannian manifolds is really, as you said, lifting the Euclidean algorithm onto the Riemannian space. Mm-hmm. I don't think I'm aware of anything. It doesn't mean it doesn't exist.
Oh, sure.
We could, have a look at that.
Thank you.
Thanks for the great tutorial. You briefly touched upon geodesic convexity. Could you provide some insight into the tools of convexity mostly associated with duality? Do they carry over, or is there, like when we have duality in the flat space, in the R space, do Lagrangian duality and stuff sort of carry over when you talk about geodesic convexity?
I'm not fully sure. So what is very certain is that the geodesic convexity is really this generalization of convexity to functions on Riemann manifolds, and as such, they tend to bring you the same tools.
Okay.
It's mostly used now for proving convergence of optimization algorithm.
Okay.
I am not sure to which extent it always brings you exactly the same theoretical properties or guarantees. It could be that in some cases geodesic convexity is not sufficient and you need something on top. I think you have to go a little bit case by case in there. It's also a very recent notion, so it has come out with the study of convergent properties of Riemannian optimization algorithm, and that started less than, I think it's 5-6 years ago when they really started having a look at that. So it's still quite new.
Okay, thanks.
All right, thank you everyone for the nice discussion. I think now we are going to move to the practical session. So we have provided a link to the collab we are aware that we are having internet issues here. So probably for some of you that you want to run the collab right now, it might not work. However, what we decided to do for the practical session is actually to show it here online with you guys. So we're going to walk you through the collab, and then maybe offline, another day you can actually play with that. And you have some questions, of course, you can reach out to us. But now what we're going to do, Noémie is going to walk you through the collab, show you kind of the optimization problem that we have there. And then if you have questions regarding implementation, just of course feel free to use the mic to ask.
Okay, let me just change the display settings so I can walk you through there. Okay, perfect. So this is basically the collab you can find on the tutorial website. You go through practical session optimization, you can open the small bar that is below and the link is there. The idea here is that we wanted to make you a little bit familiar with the Riemannian optimization libraries that are out there. So you can see a little bit how they work and if you want to apply them to your own problems. So for that, what we're doing is that we... no, I'm not sharing, right, thanks. Let me share. Now I should be sharing. Can I remove that bar? Okay, should be fine. Yeah, so what we are running here is basically the very first example I showed you as a motivation. So we are again having this impedance controller. We are giving some data and we want to basically optimize the stiffness to be able to reproduce the trajectory that was demonstrated. So here I'm just importing some packages. Collab is taking some time to import everything, but yeah. We just have to wait a little bit. The main idea here, I'm just, so the library I'm going to use is basically first implementing our own Riemann gradient descent algorithm, so you have a feeling of how you can implement that if you need. And then we're going to use PyManopt for Riemann gradient descent and other derived algorithm. Here we can also check how some second order optimization algorithm behaves. And then we're going to use GOpt, which is this PyTorch framework for stochastic optimization. So there we can test the Riemannian stochastic gradient descent and Adam. Okay, so let me still install that. So in terms of data, here I'm just actually importing some data that we generated outside. So we have some position data is the same plot that you saw before. It will come down in a second. Some velocity data, and finally some acceleration data. And I am giving the target as basically the last position data that I'm observing here. Okay, great. So we can then plot this figure. So this is, can I zoom out a little bit? Yeah, not sure how. Okay. Maybe make that smaller. It doesn't work. Okay. I mean, you see the idea. Basically, you have this trajectory, and this is the goal position that we are trying to get. Okay. And then what we do is that we define this impedance controller. So this is really the same I showed you on the slide. We have this stiffness gain. Here is the target point, which was the star on the plot above, the current position minus a damping gain, and the current velocity. So the stiffness gain we're trying to optimize, and the damping gain, either we can set it as a critically damped system, or we can set it as a constant, which basically gives us an idea on how we want our system to behave. And then when we want to reproduce a trajectory, we simply integrate numerically this acceleration that we obtain for t time step, and we see basically where we are converging. So here I just have some function that implement this point mass impedance controller. So you see here, basically this is computing the critically damped gain based on the stiffness Kp, which is provided here as input to the function. And then I'm computing the acceleration. So again, is Kp, the stiffness, which multiplies the target minus the current position. And then we have here the damping gain that we just computed above times the current velocity, right? And we return the acceleration. This function here is just a utility function to be able to implement this impedance controller as an ODE, and then we just integrate the trajectory using ODE-int, which is from torch diff ec, basically. This is really just numerical, nothing really crucial for the Riemannian part. So here what we are doing is that we are basically given a stiffness gain. Here I give it by hand, and I reproduce the trajectory, and then I'm plotting what I obtain. So what I wanted to show you here, very quickly if I can zoom out a bit. Okay, not that much. Like this, okay, perfect. And here basically this is the trajectory when we integrate the impedance controller. This is the trajectory we obtain with the stiffness gain you can see here. So here we can play around. I mean, I can change it a little bit as I want. The main thing we have to remember is that this matrix has to be positive definite, but I can play around with different values, run it again, and then see what kind of trajectory we obtain, right? So it's positive definite, but I can also put here some diagonal value as long as I put the same, run it again, and then we obtain basically different couplings of the x and y axis in terms of stiffness. So you see here we have yet a different trajectory. And you can play a little bit around with that when you open the Colab at home. By hand is a little bit of a pain to actually find the stiffness matrix that match the original one. So you can play around with that a bit. It's not that easy. So what we do is that we want to optimize this stiffness matrix. We have here this optimization problem is basically only the sum of residuals over all time steps, where we have here the demonstrated acceleration, demonstrated position, demonstrated velocity, and this is the stiffness matrix which we aim at optimizing, right? So we phrase that as a Riemannian optimization problem, and here I'm defining the cost function, and I'm defining by hand the Euclidean gradient. In practice, you can also get that automatically using differentiable package for automatic differentiable automatic differentiation. I will manage. Okay, so you can also get that automatically. I do it here by hand because it's actually quite easy to compute. So this is just the cost that you saw just here above, and here is the gradient of that cost, and both of them take as input a stiffness matrix, right? Then here we define some utility function for the manifold of symmetric positive definite matrices. So here we have the formula for the exponential map. So you see that we give as input the current point where we are on the manifold, the tangent vector, okay? And then it returns to us another point on the manifold given the formula of exponential map for the SPD manifold. And then we have this SPD Euclidean 2 Riemannian gradient. So this is basically where we are computing the Riemannian gradient based on the Euclidean gradient. And in the case of the SPD manifold, what we first do is that we symmetrize the Euclidean gradient, and then we have the multiplication on the right and on the left by the point, the base on the tangent space in which we are. And the resulting point is basically a tangent vector on the tangent space at the point here called point, literally. Then we solve this optimization via Riemannian gradient descent. So here what we do is that we set a number of iterations. Here I set 30. A step size, here is 0.05. You can play around with that also to see how the algorithm behave. And in that case, to have a simpler optimization problem, I give actually a constant estimate of the damping gain. In practice, what you could do is either in your cost function, you define it also as a critically damping gain, but then your optimization function is not convex anymore. Or what you can do is that you fix it as a constant estimate, and you can have an alternative optimization where once you optimize your stiffness parameter, then you compute the critically damped gain for that stiffness, you optimize the stiffness again, and you go like this. Honestly speaking, the main reason here why I have a constant estimate of the damping gain is that I couldn't put the square root that is needed to compute the critically damped gain in the cost function when I was using the semi-definite program in the Euclidean case, because then the function is non-convex. So I put it like that to be able to have this comparison with the constrained Euclidean optimization. But you can eventually do it better. Then what we do is that we initialize here the stiffness where we are starting the optimization. And then at each iteration, what we do is that we first project the Euclidean gradient, which we compute here, to a tangent vector, so to the Riemann gradient basically as a tangent vector at the current stiffness gain. And then we have the update step where we compute the exponential map at the current point in the direction of the gradient multiplied by a step size. Okay. Then what we do is that we compute the current cost, we plot it, and at the end of the day we plot the optimized gain. So what you can see here is the value of the iteration here on the left. Here you see the cost value across iteration, and here you have the norm of the gradient. So what you can see is that the cost decreases kind of monotonically in that way, and the norm of the gradient also decreases, and basically here we didn't converge fully, the norm of the gradient is not 0, but we are not too far, so this is why I stopped it here. And this is the optimal stiffness that you obtain in that case, right? So you see it's basically symmetric and it's positive definite directly. You don't need to do any reprojection step, any post-processing, nothing. It is on the manifold, it is valid, you can directly just use it. This is what we do here. We reproduce the trajectory, and you see that we obtain, I think it's very similar to what I actually showed you in the slides previously. So this is the trajectory you obtain based on the stiffness. Yes?
I'm sorry, but can you say why you can't exactly, if there's a ground truth, why can't you exactly capture that? Why you can't get the exact same?
Yes. So here first, there are two reasons. The first one is because I'm using a simple gradient descent. So it's not the best algorithm. You could use something a little bit more powerful.
You started with the exact solution of the trajectory.
Yes, it would. Not exactly in that case, because I'm putting now, so the trajectory was generated with a critically damped gain, and in this case, I'm fixing the gain. So if you have the exact stiffness, you still have the damping that is not necessarily exact. If you put the critically damped gain in the cost function, yes, then if you have the ground truth, you have exactly the same function. Does it answer your question? Good. If there is any other question, just feel free to interrupt me. Yes, okay, please. Yeah.
If you would increase the number of iterations there from 30 to a higher number,
yes,
you get closer then to the green curve?
So in principle, yes, we can try it. Let me put 50. What could happen is that I have a constant step size, and then maybe my step size is making me, jump from one. So if you want to do something a little bit smarter, you need an adaptive step size. But let's check. I put now 50. So yeah, actually in that case, yes. So you see here we have all of it. The cost continues to decrease. The norm of the gradient continues to decrease. So you could increase it. If at some point you start jumping, it's because of the step size. Yes?
I guess I'll stand up. Can we just go back to the cost, the STPX map?
Yes.
I guess I just don't remember off the top of my head. So why is there a least squares problem being solved to find the P inverse TV? And then my next question is where does this STP Euclidean to Riemannian gradient, I just don't remember that math, I guess. Could you just remind us?
Can you say that again? Sorry.
So my first question is why is there a least squares problem being solved in, you do np.lineage.solve, you're solving a least squares, like it's an AX equals B problem.
Yes.
So I just don't remember that. And then, what's the motivation for the definition of the STP Euclidean to Riemannian gradient?
Yes, okay. So for the first one, this is actually, so the linear solve is just to solve this problem. This is the definition of the exponential map on the SPD manifold, basically. Here I solve it with the solve problem because on the mathematical explanation you have something on the form x minus 1 times another matrix, so you can just solve it like that. It's numerically more efficient. You could just also do it like numerically inverse of the matrix times the other thing. It really comes from the definition, from the the operation of the exponential map there. For the SPD Euclidean to Riemannian gradient, this is at the moment where we want to compute the Riemannian gradient on the SPD manifold, where basically we start from the Euclidean gradient, and I think this is related to the question you asked previously, where you use either the inverse of the metric times the Euclidean gradient, or you use it as a projection. So here we actually have a projection, and yeah, this is to compute the Riemannian gradient from Euclidean gradient. Thanks. Any other questions on that part? Yes.
Do you have any experience, like I saw, or this example is using the semi-definite cone, and then do you have any experience, for example, if I imagine trying to fit an inertia of, let's say, a 7-axis robot, then you have at least comparatively a high-dimensional, quite complex structure. Do you have any experience if this still converges, or are there any numerical problems then?
So we actually had some experiments like that in the Bayesian optimization paper, where we use Bayesian optimization for that kind of things with black box functions. That worked fine. In principle, it's the Riemannian optimization scales better to increase dimension compared if you also used constraint optimization on Euclidean spaces. So you still increase your dimension, it always becomes a more complicated optimization problem, but compared to using constraint optimization in Euclidean spaces, the Riemannian one scales better.
Okay, thank you.
Thank you. Okay, let me continue. If there is any other question, just feel free to interrupt me. I'm here checking the computer, but just interrupt, really. Okay, so here is what we obtain when we have the stiffness gain found by our simple gradient descent algorithm. And now, basically, we want to do the same thing, but to show you a little bit how those optimization library work, here with basically PyManopt. So here what we do is that we use this PyManopt library. So the first thing I'm doing, I'm importing it. In PyManopt, when you define an optimization problem, you have to import this problem structure. Then we have a set of manifolds. So here I'm importing the manifold of interest for this problem, the symmetric positive definite one. And here I'm importing a bunch of optimizers, which we can test basically in our case. Then with PyManopt, what you do is that first you create the manifold of interest. So here is a symmetric positive definite manifold of dimension 2, which is what we have there. And then we create a cost function. So PyManopt can use different backends. You can use PyTorch, TensorFlow, NumPy, and I think there's the last one, which I forgot. And basically you choose which one you want to use, and you decorate your cost function with the backend you choose. So here I do it with PyTorch. And then, again, I give here my constant estimate of the damping gain, and then I return a cost, right? The same cost as before. Then you create a PyManopt problem. So in the problem, you give the manifold of interest, which I defined just above, and you give your cost function. Then you instantiate an optimizer. Here I just take the conjugate gradient. Yes?
In your talk, you said you would find the current gradient and you would remember the one previous step. Does having gradient require you to remember more than just one previous step you have to remember?
So conjugate gradient remembers one.
Just one?
Just one, yeah. So this is exactly the conjugate gradient, the one that we presented on the slide before, where indeed we remember that step. It's exactly the same algorithm. Okay, and then what you do is that you run basically your optimizer on your problem. It gives you a result, and the result you get the point, so the optimal stiffness in our case, and you get the optimal cost. And here what I'm printing is basically the evolution of the cost over the iterations. So PyManopt is cool because you also have some optimal convergence. So here I don't need to say how many iterations I want to run through. It just stops by itself when it reaches some convergence. So here you see that we go through 52 iterations. This is here the final cost. And you see that after 52 iterations, this is the norm of the gradient is very, very tiny. So this is basically where we converge. Here I'm printing again the optimal stiffness, and we can plot again the trajectory. And what you see is that we actually have a trajectory that is slightly better than what we had with the simple Riemann gradient descent. So here we reach almost the target, and the shape is a little bit closer. Any questions on that part? Yes?
So here you're not specifically constructing convex optimization blocks, right?
No.
But does pi out have like similar to convex, let's say another convex op? Is there a way to like compose a problem so that you know it's a convex optimization problem or use specific algorithms that are
So PyManopt itself doesn't really check if the problem is convex or not. Here you define your cost yourself, you choose your optimizer yourself. So no, it doesn't have that.
Are there any libraries that you're aware of that use convex optimization methods for online tools?
Not as far as I know, no. So you don't have, it's true that very often in the Euclidean case, as far as I know, you try to transform a problem into a convex one so that you can apply your constraints and basically you obtain more efficiently your solution, right? In that case, you're already constrained on your manifold, so you don't have an additional constraint on top. And because of that, then you can just run the usual algorithm without caring too much of getting your convex objective function. If you have something convex, of course, you have better convergence properties, but you don't have the same kind of need for that, in a sense. Yeah. So you can also do that. PyManopt doesn't have them. There is an implementation of some of those approaches in MATLAB. What is out there is basically generalization of penalty methods from Euclidean to Riemannian manifolds. So typically where, yeah, penalty constraints and that kind of thing. You're welcome. Any other questions? Okay, let me move on then. Okay, so the last one, we are still optimizing the same impedance, but this time with the library GOpt. And here we are interested in using stochastic optimization algorithm on manifold, basically. So here what I'm doing simply is that I import GOpt. It's very the same principle as PyManopt. We import the manifold, and then we import here a manifold parameter and a manifold tensor structure, which I will show you how to use. And here I'm importing Riemannian Adam and Riemannian stochastic gradient descent, right? You can use any of them. Cost function here, you don't need any decorator. GOpt is fully PyTorch based, so this is what you can define there. And then we here define our parameters. So in that case, GOpt works pretty much like the PyTorch optimizers. So in that case, you don't have those automatic convergence detection. You actually have to give your number of iteration. And here you give your step size. Then you instantiate your manifold, and this is where you actually have to start doing with GeoP tool. When you initialize your initial point of your optimization, you have to define basically a manifold parameter, right? And you tell on which manifold, which is the one I just defined, you tell on which space this parameter is lying. And then you define an optimizer, Riemannian Adam, and what GeoP does in the background is that it checks that your manifold parameter belongs to the space of symmetric positive definite matrices, and in the Riemannian Adam, it uses all the operation that you need to compute the Riemannian gradient, the exponential map, the parallel transport, and everything you need. So this is done for you in the background if you define this point as a manifold parameter. You can also here simply define products of manifold. If you want to optimize at the same time something that is Euclidean and something that belongs to a manifold, you define it as a manifold parameter on a product of manifold, and that also works out. So you can, when you have a mix of things you want to optimize, you can still use this. And then the loop is very much like in PyTorch optimization stuff. You compute the cost, then you do cost.backward, this computes the gradient, and then you do a step of your optimizer. Right. Here then I'm printing again the cost. Not sure if I run it or not. Yeah. And you see that here again the cost is decreasing. As opposed to before, you see that sometimes the cost goes a little bit up and down. This is because of the stochastic part, right? So we have this, this stochastic part that basically makes the costs oscillate a little bit. We have again here the optimal stiffness, and then we can reproduce the trajectory. And in that case, you see that the stochastic part actually is useful because this is probably the best curve that we actually recover. Yes?
You were using a fixed step size here. Is it
Yeah.
possible to adapt the step size during iteration?
Yes, you can do that, yeah. So the step size here appears in the optimizer, I think. Yeah, I give it as a parameter to the optimizer, so you could change it in the optimizer, and then continue to run your loop. So this is possible, yeah. Yes?
I noticed that the cost now is 22, and before it was like 20. So did we redefine the cost?
The cost is the same. So yeah, actually this is a good point. It's very similar. It's true, it looks better, but the cost value is actually a little bit higher.
Okay, so it looks better, but it's not.
Yeah, right. Good catch. Yes?
I guess you have to maximum points of time, as well as when you put two curves laying on top of each other, it would still not be zero with the box.
Yeah, exactly. With this damping gain that is fixed, it wouldn't be exactly zero. If the damping gain is critically damped, then yes, it would be zero. Okay, so if there are no other questions, I think we can close the practical session here, and now we will have our first invited talk.